A second shot. Afternoon, everybody. All right. It's a little bit better. I'll ask it again later so that let you warm up a little bit. Welcome to Mysteries of Windows Memory Management Revealed. My name is Mark Russinovich. This talk it was jointly developed by me and Dave Solomon. Dave Solomon, my co-author in the Windows Internals book series. Last book edition, actually, we had a third co-author, Alex Ionescu. But this content has been evolving over 15 years since Dave first started teaching Windows Internals, and it's evolved tremendous amount since then. With some of the tools that I'm going to show you this afternoon, you're going to get insight into the way Windows uses memory that basically has not been possible up until very recently until these tools were released. So it's more than just the theory. I'm going to be showing you in practice what's going on underneath the hood. Before I start, though, into the talk, just let me mention a little bit about what I'm doing at Microsoft. I've been at the company for 4.5 years. Prior to that, I had a software company called Winternal Software and a freeware website called SysInternals. Both of those were acquired, and I joined Microsoft. Is that Winternals or SysInternals? SysInternals. Any Winternals fans in the room? Yeah, a few. Okay. Any MDOP, MS Dart fans? It's a name that only an NT geek could love, MS Dart. But the previous name was just as bad, ERD Commander. So I joined the Windows division, and I worked on the tail end of Windows Vista, Windows 7, and then after Windows 7, worked on figuring out what was going to be in the next version of Windows, which I can't mention its name, even though you probably already figured out what it is, but I'd get in big trouble. So we're supposed to say Windows V next, and you're not supposed to be able to figure out what that really means. So I started talking to some people in the cloud division, including one of my heroes, actually, from before I even got out of grad school, Dave Cutler, who was the original architect of Windows NT and VMS and RSX11M. He left the Windows division right after I joined it to start Windows Azure, back then called the Red Dog Group. And he saw the cloud as the future of the company. And I talked to him and some other people over in the Windows Azure team, and I'm convinced the cloud is the future of the company as well. It's the future of where everything is going, the cloud connected by devices. That doesn't mean anything I'm talking about here is less important. In fact, when you're talking about things that run in the cloud, what are they running on? They're running on operating systems, and they're running in virtual machines. And everything that I talk about here that applies to a client or a server, a physical server, applies to virtual machines on your local VMware systems or Hyper-V systems, as well as whatever you run up in the cloud on EC2 or Azure. So in any case, I've been on an Azure team for the last 6 months or so, and I'm having a blast in Windows Azure. It's like we're creating Windows 3.1 for the future, and I got in on the ground floor, which is pretty exciting. So I'm giving a talk on Windows Azure tomorrow, by the way. But I haven't forgotten this stuff, and I will still continue to talk about it. And so this afternoon, I've got a 2-part session for you. This first part is going to focus on virtual memory, process virtual memory, and process system virtual memory. Let me switch over to the right screen here. And so the goals of this are to do 2 things. One is to take you deep into process memory usage, and then take you deep into system memory usage at the virtual level, and then follow that by taking a look at the physical level as well. 2 completely distinct ways of looking at memory management, virtual and physical, with very little connection between the 2. Right at the connection between part 1 and part 2 of these sessions, I will show you the bridge between virtual and physical, which includes how do you size the paging file. That's one of the things that you're going to learn this afternoon, how to figure out what the right paging file size should be and what exactly Windows uses the paging file for. Another goal of this session is to try to define some terminology that means something and that is consistent, hopefully as much as it can be, across tools, and terminology that I'll establish so that when I say something, you understand what I'm saying. One of the problems with understanding this space is that there's so many different terms used for the exact same thing or variants on the same thing that it makes it very difficult to look at a tool, look at what the label is, and understand really what it is, because on a different tool, even in the same version of Windows, they'll call it something different. And so I will try to clarify the meanings of some of those labels that you see. And then I'll conclude with looking at some of the dark spots of Windows memory management, some places where you can have memory resource usage, either physical or virtual, without the ability to really easily figure out what's causing it. And that's, you could say that's a limitation in Windows, but I wouldn't say that because I work at Microsoft. So I will say that it's very difficult to get that connection back. And actually trying to make that connection, it hasn't surfaced as a priority because not a lot of problems occur in that area with having to connect it back, and it would be a tremendous amount of overhead on the system to keep track of things in a way to make it possible to connect it back. So in any case, that's the conclusion of part 2. So just in case you were thinking, I'm going to ditch this right after part 1 and not come back, you're going to be missing physical memory management as well as the dark spot stuff. Here's the actual breakdown of the agenda. I'll start by address space usage, talking about the components in a process address space. Then I'll talk about process commit memory, process committed memory, then system committed memory, how process committed memory relates to system committed memory, the implications on the size of the paging file. Then, like I said, part 2 is physical memory, taking a look at working sets, which is the physical memory assigned to a process and the way Windows manages that memory assignment. And then paging lists, how it keeps track of all the memory in the system on various lists. The tools that I'm going to use in this 2-part session, I'm going to show you Task Manager, of course, because that's one of the tools that's commonly used by people still today, unfortunately. I'm going to show you the tool that you should be using instead of Task Manager, which is Process Explorer. I'm going to show you VMmap, a tool that will let you take a look inside of a process at a very deep level to see how it's using memory, both at the virtual and physical level. Another tool called Rammap. How many people have used Rammap or VMmap before? Just curious to see how many people are already familiar with them. So just a few hands. So these tools will be new to most of you. And I'll also be using a tool that's a pseudo tool. It's just a demo tool called Testlimit, which is a tool that I've written that will stress the system in various ways. And I use that tool to highlight certain behaviors of Windows in a very easy to understand way. All of these tools are free at sysinternals. And by the way, I forgot that I need to connect into a machine at work, so I'm going to disappear here for a second while I pull out my smart card so I can TS into a machine. This laptop is a little anemic, so I don't have virtual machines running on it. Besides, virtual PC isn't the best kind of virtualization tool. So, and I can't run one that's better, as you could imagine. So I'm going to TS into a server at work running Hyper-V. And the network was working just a second ago. Please turn off your wireless devices. All right, well, oh, here we go. All right, while that's coming up, I'll come back to that in a second. Let's talk about virtual memory. And this slide is just about some of the fundamentals of virtual memory management. First of all, Windows is what's called a demand paged memory management system. What demand means is that a process doesn't get born with everything it needs. It actually asks the system for it. It demands the system for what it needs. That's most clear in the context of physical memory management, where when a process allocates virtual memory, that virtual memory is just a concept until the process touches that virtual memory, demanding that it be backed with something physical that it can actually put its hands on. And the paged part of it is the fact that memory is managed at page size granularity. The page is defined by the hardware, and sometimes in conjunction with the operating system, also defining it. There's no swapping in Windows at a process level, and that was a memory management technique used in some older operating systems, including some variants on Unix, where when a process went to the background and got idle, the system would just take its entire memory and throw it out onto the paging file, and then swap it back in. A page on Windows systems is 4K. The default page size is 4 kilobytes, except for on Itanium, which there's some references to Itanium. Anybody have to use an Itanium in here? Anybody ever used one? Few? You work for HP? Yes? Itanium it's a fantastic processor. You know, x86 and x64 do a lot of things really well. Itaniums do a couple things even better. In fact, that reminds me, if anybody needs a doorstop or a heater, let me know, because I've got one that's really cheap. Anyway, so that's all I'll say about Itanium. I'm just kidding. I've got a doorstop that also doubles as a heater. It's not an Itanium. So sorry about the misleading you there. Another aspect of Windows memory management system is that allocations have to happen on 64 kilobyte boundaries. And that's important because one of the tools I'll show you will show you the gaps between an allocation and the next granular boundary, because that is essentially wasted address space. So if you allocate 4K, then that next 60K is basically off limits because you can't allocate at a sub 64K granularity. There's also large pages, and this is where Windows interacts with the hardware because it can dictate the size of these large pages. The hardware a lot of times lets you set the size. On x86, the large page size is 4 megabytes. On x64 and x86 PAE, it's 2 megabytes. And the reason why Windows uses large pages and actually makes use of them in a number of scenarios, one is to map the kernel and boot drivers into large pages of physical memory, is that improves performance. Because when you have virtual memory and physical memory, there's tables, page tables, that map virtual memory addresses to physical memory addresses. And that translation goes through several steps, and that's a slow translation. And so processors have something called a translation look-aside buffer, a TLB, that caches the translations. Now, if you take a chunk of memory that's 2 megabytes in size and you allocate it in 4K chunks, then to cache those translations would take 2 megabytes divided by 4K number of entries in the TLB. And that puts a lot of pressure on the TLB. If you map that 2 megabytes with one 2 megabyte large page, then you only need one entry in the TLB to cache that translation. And so you've optimized the performance of the system by having that translation of that address range not impact the rest of the system. So, and applications can take advantage of this as well. There's virtual allocation APIs where you can specify you want large pages. Now, I want to really emphasize this point, that there's no connection between virtual memory management and physical memory management when it comes to understanding the way the system works. Well, actually, there's one exception. So I almost know there, and that's the bridge that I've talked about that relates to the size of the paging file. But important to keep in mind that this first section of the talk is totally about virtual memory, not about physical memory. It has nothing to do with how much RAM you've got. So let's take a look at the address space layouts now on 32-bit and 64-bit systems. This is 32 bits. 32 bits is enough to describe 4 gigabytes. So that's the size of the address space of a process. That address space is split in two by default. 2 gigabytes, the lower 2 gigabytes, which is always shown on the top of the picture for some reason, 0 to 2 gig is owned by the process, and 2 gig to 4 gig is owned by the system. That when each processor has a current process mapped on it. So the page translations are per processor. That means that you could have a Notepad thread on processor 0 and a PowerPoint thread running on processor 1. And that means on processor 0, you'd have Notepad's address space at the top of the picture there. On processor 1, you'd have PowerPoint's address space at the top of the picture. When there's a switch on a processor, like the system switches from a thread in Notepad to a thread in Excel, you would have a switch of that top part. The bottom part remains fixed, and that is also a performance enhancing trick to have the system share its address space with the process, because that makes it easy to transfer data back and forth and to reference data without copying it. So if somebody wants to do an I/O and they say to the system, send this block of data to the disk, the system can, instead of copying that data into the system address space, it can just simply reference it directly from the user's address space and send it out to the disk. On the right side, you see a variant of that 32-bit gigabyte address space, which is the 3GB, or 3GT it's called officially, 3 gigabyte tuning. This was introduced in Windows Server Enterprise Edition Service Pack 3 back in 1990, 8, I think. Anybody correct me on that one? 1998, SP3, NT4? Oh, thank you, Mr. Manassi. I knew you would know. You know all that stuff, all that trivia, arcana from long in the past. How far back does that go? Sorry, I didn't mean to offend you. I respect your old age, sir. All right, let's move on. So this 3GT thing that was introduced lets you specify in the boot.any switch back then a /3GB, which would move the line down to 1 gig for system, 3 gig for user mode. And the reason why you would want to do that is that there are some virtual memory intensive applications that, like, yeah, Squeal Server, you call it Squeal Server, don't you? Yeah. SQL Server is a great example. And Active Directory Domain Controllers, the LSASS process is another example that takes advantage of this, where when they're accessing or managing large amounts of data, it's more efficient for them to do it in bigger chunks like this. Let me give you an example. SQL Server that has a 4 gigabyte database, if it wanted to read the whole database into its address space, well, actually make it 2.5 gigabytes. Let me do that. 2.5 gigabyte database. If it wanted to read the entire database into its address space, it couldn't do it with the mapping on the left. It just doesn't fit. With the one on the right, it can do it. With the one on the left, what it would have to do is basically swap out parts of the database and never be able to access the whole thing at any one time, and that swapping can affect performance. On the right side, it just sucks the whole thing in or maps the whole thing into its address space, and it's done with it. Now, 64-bit. 64 bits, in theory, could address up to 16 exabytes, that 17179 number. But today's x64 processors have a limitation of 48 bits of virtual addressing, which limits it to 256 terabytes of address, virtual address space that can be used at any one point in time. And actually, 64-bit Windows supports only 44 bits of that. So it supports up to 16 terabytes of virtual memory. And if you look at the split, it splits that 8 terabytes for user mode, 8 terabytes for kernel mode. And so you can map a whole lot more stuff into it. At that point, SQL Server, for the time being, doesn't have to worry about swapping things back and forth. Outlook may have to, but SQL Server is fine. And if you look at the right side, that's what a 32-bit process looks like on 64-bit Windows. Actually, one of the things back here is that to take advantage of that extra 1 gig there on the right side, you've got to have an image that's marked as large address space aware. I've got such an image. I mentioned Testlimit. And if you dump bin, which is the linker tool that comes with Visual Studio, and dump headers on Testlimit, you'll see here that one of its characteristics is application can handle large 2 gigabyte addresses. So on 32-bit Windows, if you booted /3GB, Testlimit would actually be able to use it. And on 64-bit Windows, as you will see, Testlimit gets full 4 gigabytes. So any large address space aware app on 64-bit Windows can get just a solid 4 gigabytes. It doesn't need to split that with the system because the system's got its own 8 terabytes down there. Now let's take a deeper look inside that address space and talk about what's mapped into a process address space. There's 2 terms that I'm going to introduce here. One is committed and one's reserved. Committed part of the address space means that it's in use. It's actually doing something. It serves some purpose. It represents some data. Reserved means it's reserved for future use. It can't be allocated again. It can be committed. You can transfer or morph reserved memory into committed memory, but you can't allocate it from it again. So in other words, if you do an allocation, Windows will, unless you tell it where in the address space you'd like that allocation to come from, it will just give you its own idea of what it thinks is the best place for it to come from. it will never allocate from reserved because you've said, I'm reserving this for later commitment, and so it won't allocate from those regions. And I'll talk in a little bit about why reservation or reserving memory is interesting. When you take a look inside the address space, there's 3 types of memory: private memory, shareable memory, and free memory. Private memory is memory that represents data that's just for use by the process. A great common example is the heap. Every process has a heap that the language runtime will allocate from. When the process wants to allocate a variable or a data structure, it comes from the heap. That's private virtual memory. The shareable virtual memory are parts of the memory that map files or data that can be shared with other processes. And there's several types of that. One is shared memory. So a process can allocate memory and say, this is shared memory. And then another process can map that shared memory in its own address space, and they can talk to each other through that common mapping. So if one writes to that memory, the other one will see the contents of that in its address space when it reads from it. So it's a high-speed inter-process communication mechanism. Another type of shared memory or shareable memory is images and map files. Images, of course, being DLLs and executables. If I load Notepad into my notepad.exe into my process, and another process also loads notepad.exe, well, that is shared. Those mappings are shared because that other notepad will map the same underlying data or code that I've got mapped into my address space. And the same thing for data mappings. I can also map data into my address space from disk, files on disk. Like if I have a .ini file, I don't want to suck the whole thing in because it's huge, I can map it into my address space, and I'll talk more about that in a little bit as well. And then free, of course, is undefined. Now, most allocations are just pure, just give me this amount of memory because I know what I'm going to do with it. But there are cases, like I said, where reservation is interesting and makes a lot of sense. It lets an application lazily commit contiguous memory. In other words, if I'm allocating some data structures when I grow the data structure, it needs to be contiguous in memory. The addresses need to line up sequentially. But I don't know how big, for sure, that data structure is going to get. What I can do is allocate the minimum size and then reserve a chunk of virtual memory that I think that the data structure might grow to. And then as the data structure grows, I just commit chunks of it. A great example of this is stacks. So every thread that executes on the system has a stack, a private scratch space where it stores parameters that it passes to other functions and local variables. And when the stack is born, the system virtual allocs a chunk of memory from the address space. By default, it's 1 megabyte for most processes. And then it will lazily commit that stack. So it commits just the initial part of the stack. And then when there's a guard page there that it allocates past that, and when the stack grows and touches the guard page, there's a fault. The memory manager intercepts that fault and says, time to expand the stack. And what it'll do at that point is deallocate the guard page, move it to the end of the next expansion, and then commit the memory that was reserved there. And you can see on the right, so it's moved the guard page, committed some more of that reserved memory, and the reservation that's got left shrinks. When it runs out of that reservation, the stack is fully done. It can't grow anymore. As far as tools that will show you what's going on with some of these things that I've just talked about, Task Manager only lets you see private bytes. Private bytes being the data that's private to the process and just can only be private. And before Vista, that column showed up as VM size. On Vista and later, the column is called commit size. But unfortunately, Task Manager, when you start it, doesn't even show you that column. It just shows you this one, which I'll talk about in the second part. So it's not showing you that, and you need to add it here. And it is commit size. So if I sort by that, this is the private bytes allocated by each process on the system. PowerPoint having roughly 140 megabytes of private bytes, which makes sense. It's probably read and created data structures representing that PowerPoint in its address space, stored them in private allocated virtual memory. Process Explorer shows you both virtual size and private bytes columns. And actually, this is a place where you can see some confusion start to show up in terminology. Here, the change in terminology here from VM size to commit size, but when commit size is really private bytes everywhere else in the system. If you look at perfmon, it's called private bytes. If you look at Process Explorer, it's called private bytes. And in most cases, when I had a choice, I went with what perfmon decided because that's the low levels of the system's definitions of things, not task manager. And VM size sounds too much like virtual size, which is what Process Explorer shows you is the total amount of the address space that's either committed or reserved. In other words, the total amount of address space that's in use. So here I've added the virtual size column and the private bytes column. And what I'll do a little experiment here. I'm going to run 2 instances of Testlimit. One that just reserves memory with Testlimit-R. It will reserve as much memory as it can. And you can see that it was able to reserve just about 4 gigabytes because it's marked large address space aware. It's on 64-bit Windows. And that's as much as it could reserve before its address space got totally filled up. Let's run Testlimit-M, which allocates private committed virtual memory, in other words, private bytes memory. And here we're seeing the paging file grow. So it actually allocated close to 3 gigabytes, and now we know that it can get close to 4 gigabytes as well on this, but the paging file is too small, and it's going to grow here. And Windows actually sees that and says, hey, actually, I can't zoom for some reason. But it says that computer's running low on memory, and it's Testlimit that's doing it. I'm not going to close it. I'm going to just say, yeah. Let's go back and so you can see the system's acting a little funny, which that's a demo I wanted to save to later, but it's happening early. And normally what I do is I pre-expand the paging file, but as you'll see later, the paging file can shrink again. Let me pause this. Let's see if my system can come back. Process Explorer just died on me. No, there it is. All right, so like I said, this wasn't supposed to happen this early. You're seeing the effects of virtual memory running out on the system. Yeah, reboot, no. No, we don't have to reboot. We can do this. There, everything's back to normal. So actually, let me do this. I'll do Testlimit-M1024 to leak 1 gig instead of 4 gig. And I'll do the same thing on Testlimit-R. And by the way, I'm Control-Cing here. I'm typing Control-C, but you can see nothing's happening. And that's because the Control-C handler actually has to allocate some memory to respond to the Control-C. And memory allocation fails because the address space is full, and so no response to the Control-C. So let me run a new instance, Testlimit-R 1024-C1. And now let's go back into Process Explorer. Sort by process column. And now here's my 2 test limits. And let's see if we can tell those 2 apart by looking at the virtual size and the private bytes columns. So here's the 2 test limits right here. Now, which one is the one that committed memory? First one, right? The top one is. The bottom one just reserved memory, so that it didn't allocate any private bytes. The top one allocated private bytes. You can see it allocated 1 gig. Now, virtual size-wise, the amount of their address spaces that are in use are the same. One just reserved all that memory. The other one actually committed it. So one of the reasons that Task Manager used to show you that VM size and which later, what did it call it later? Commit size counter by default was that most memory problems caused by a process are them leaking private bytes. That's by far the most common type of system impacting process problem, is they allocate data structures and they don't free them. And you end up with this leak that eventually ends up not only just impacting that process, because as you can see, it ran out of address space. That caused the process to usually crash. But it also can impact the rest of the system. As we saw the paging file go up in size. And I'll talk more about system commit in a little bit and why that happened. But that's the #1 cause, and so that's why private bytes is such an important counter. But private bytes only tells part of the story when you really want to understand what's going on with the virtual memory usage of processes. It doesn't account for shareable memory that's not shared. If you're interested in what is this process really, what is its impact on the system, how much virtual memory is private that it's using, how much is shareable, what is that shareable? And this is interesting from a developer perspective as well, when you're looking at optimizing your own code, that if you've got shared memory but you're not sharing it, it might as well be private memory. Shared memory is only useful if you're sharing it. The same thing goes with images. Images won't show up in private bytes. If you've got foo.dll, but you're the only process that loads foo.dll, it doesn't show up in private bytes, and yet foo.dll's impact, its code and data that's mapped into your address space, that is impacting you and nobody else. It's not like you're sharing that with anybody else. Also, fragmentation can be an issue. Fragmentation of the address space means that you get this allocation pattern over on the right where you end up with holes between the allocations. And now you can't allocate anything bigger than the biggest hole. And that biggest hole might be far less than the sum of the sizes of all the holes. So you go look and see private bytes is low, and yet this thing is really out of virtual memory already, failing to allocate virtual memory, and that could be because of fragmentation. A real-world case where this was a major problem was during the development of Visual Studio Dev 10, the Visual Studio 2010 release. You know, they rewrote the entire editor in WPF. And so that moved it to managed code. And when you're writing managed code, you need to be careful about memory management. Unfortunately, a lot of people that say managed code, well, now I don't have to worry about memory management. The CLR is doing it for me. And everybody forgets how to free memory. What they don't realize is that you still can leak memory through cycles. And you can also end up with address space fragmentation, depending on how your allocation patterns work. Visual Studio ended up running out of address space because of fragmentation. So to take a deeper look, like I said, we're going to take a look at VMmap and take a breakdown at a very low level inside of a process. And that process, my favorite process on the system, is Notepad. So I'm going to run Notepad, and we'll take a look at what's going on inside of Notepad. Now, how much of Notepad's address space do you think is in use? Anybody want to take a guess? I just launched Notepad, didn't load anything. It's just a simple text editor. Can't even save RTF format, which is really ridiculous. But 7 meg? 20 meg? 4 kilobytes? This isn't DOS. 1 meg? Answer is? Oops, what did I just do? Oh, I closed it by accident. Let's do that again. Just as you were about to see the answer, I pulled it away from you. All right, and it's 53 meg of it is committed. Now, that's not as bad as it looks. It's almost as bad as it looks, but not quite as bad. Now, so let's take a look at this breakdown of what it's got committed. Remember, committed is in use. And these colors up here in the bar correspond to this table down here. So the purple is images. That amount of the roughly a little over half of what's in Notepad's address space corresponds to images, DLLs, and the executable itself. If we want to take a look at how much is dedicated to images, 30 megabytes of that 53, that number right there, is committed images. Now, you also see this column, which is private. This is the private bytes of the particular regions of virtual address space that correspond to images. And you're probably saying right now, hopefully you're saying, why is there private bytes inside of these image mappings? It has to do with parts of images being marked copy on write, which is what I'll talk about a little bit later. It's where the image has data that can be modified by the process. And you want only that process to see those modifications. And so this mechanism called copy on write makes it possible for Notepad to modify that, but Notepad to be the only process, this instance of Notepad to be the only one that sees it. If another Notepad starts up, it will not see that, but it will see its own modification to that same area. Example for this are global variables. allocated, defined in the image. If Notepad modifies that global variable, it needs to store it, and it stores it in that mapping. But the second Notepad that starts up might define something different for that global variable. So that's the bulk of it. And when you click on one of these lines in the top part, you filter the low part. The bottom part is the actual address space complete layout, starting from the very lowest address, showing you just the parts of the address space that have allocations. So I'm going to filter on images, and this will show us now all the images mapped into Notepad, including where they're mapped into the address space. Now, each mapping region can consist of subregions, and I'm going to split open one of these subregions because in an image especially, there's many subregions. There's the header of the file, the code of the file, the relocatable data section of the file, the copy on write data section, read write data section, which can serve as shared memory, copy on write additional data section here, and those are mapped into different regions, which of course have different impacts on this size. If you sum all these up, it sums up to the size of that header block right there. The next is map file. Map files are these data files mapped into the address space. You can see NLS and data files here. These are technically shareable. Their size is here. They're committed, and you should rarely see private here because shareable means you really did want to share it. If you wanted private, you would have probably said private. And speaking of private, let's move down into some of the private areas. So these top three are all shareable types of memory. These bottom ones are all private. Heap, I mentioned heap. So every process in Windows defines a number of private heaps. And those heaps are allocated in large chunks or reserved for the most part, and then they grow as data gets allocated from the heap. And so if we break this open, you can see a great example. Wherever you see a difference between size and committed, well, size and committed, that difference is reservation. So 1 megabyte of this heap was allocated. Most of it is reserved, only 128K is committed. And if you split this open, you can see here 896K reserved. The other 128K is actually the part that's in use. So that's another great example of where the system uses memory reservation. Managed heap, this is if, how many people here program .NET stuff? So I'm surprised you're actually even in this room if you do that, but I'm proud of you for coming. But let me run something that uses a lot of managed heap, MMC, and should give you a quick look at what VMmap will show you for something like that, even though I'm not going to dwell on it. If you're doing it, managed code, low level, memory analysis. This is, oh, why am I not seeing managed heap? All right, never mind. I'll show you that another time. Oh, it's because I didn't load it snap-in. Never mind. I need to load a snap-in. Do you want to see that, by the way? All right. All right. Now we should see some managed heap. Since the MMC is elevated, I need to elevate too. VMmap. And it's actually taking a while because it's doing this managed heap. There's managed heap. And when you click on that now, you can see it breaks it down into exactly what's going on inside the managed heap, including reservations. It also uses reservations, low frequency heaps and whatever, blah, blah, blah. All this stuff that I barely know anything about, but I'll pretend like I know a lot about it. See, because I'm showing it to you. So back to this. That's managed heap. Stack. I mentioned that stacks you make use of reservation. Notepad doesn't need a 1 meg stack. Its initial thread only needs 512K, so it requested that. And you can see now we've got, here's the reserved, 432K. Here's the guard page, and here's the top of the stack. The stack grows down, and it's 68K of it has been committed. So when it ends up touching this, then boom, it's going to grow. And actually, we'll come back to that. That is thread number 12. Somebody remember that thread ID, because we'll come back at this and look at this thread after I perform some operations and see how if its stack grew. And then we've got private data. Private data is the generically kind of virtual allocations. It's just calling the raw virtual alloc API. In fact, most of these private allocations underneath call virtual alloc. The heap manager calls virtual alloc, but then subdivides these virtual allocations. This is just basically the process just saying to the system, just give me a raw chunk of virtual memory and I'll deal with it myself. And so that's what Notepad has done with these. Obviously, completely private when it does a virtual allocation. Page tables, this is the charge on the system, has more to do, not on the address space, but on the system, has more to do with the system commit limit that I'll talk about, of just creating the page tables to describe the address space of the process, what's currently it costing the system. And then finally, here's that unused section, unused, which shows you remember those gaps I mentioned between the allocation and the end of the allocation size show up as unused here. And Notepad's got roughly 1.3 meg of its address space that it's basically can't use. It can't commit it. It can't reserve it. It's just sitting there in kind of limbo at the end of allocations. Let's select one of these and then look at what it abuts to see. To see those allocations, you say show free and unusable sections. So there's shareable memories allocation right here, which was 24K. 24K was committed, and that means that that 40K following it is unusable. So that's and finally, down here at the bottom, you've got the amount free. This is a 64-bit process, so it's got a lot of address space free. Close to 8 terabytes. We'll never use that. Nothing will ever need that much. So speaking of fragmentation, like I said, fragmentation happens when these chunks of memory in between allocations are smaller than the amount of memory that you want to allocate, and you end up prematurely not being able to allocate memory because of the fragmentation problem. In fact, I can use Testlimit to trigger a memory fragmentation issue. Let me launch a new Testlimit here. And I'm going to launch Testlimit-T. This is the 32-bit Testlimit trying to create as many threads as it can. Now remember I said a thread has by default 1 megabyte. So this Testlimit has close to 4 gigabytes of address space here for its use, but yet it was only able to allocate around 3,000 threads. It should have been closer to 4,000. So something went wrong here. Wasn't able to allocate as many threads as it wanted. Let's take a look in VMmap at what's going on with that Testlimit. Now, if I go down to the threads, the stack area, whoop, did I opened the wrong one. Testlimit. Yeah, this one's taking a second because it's got so much data to chew through with all those thread allocations. Here we go. Now, scrolling through here, you can see that there's stacks that are 1 meg in size, and then there's these other stacks that are 256K in size. This is what you'll always see on a 32-bit process running on 64-bit Windows. Actually has 2 stacks. One is for when it's in 64-bit mode, and the other one's when it's in 32-bit mode. So as far as Notepad's concerned, it only sees the 32-bit 1 meg stack. But when it calls into the system, like it makes a system call, it's going to switch onto a 64-bit stack before it heads into the system, and that's what that smaller 256K is. So for these process now, to allocate stack for one thread, it needs 1.256 megabytes. So divide 4 gig by 1.256, we still should have more than 3,000, be able to allocate more than 3,000. In fact, if you go to the sort, the free column and sort by size, well, the largest chunk that we have is 896 kilobytes. Even though there's 376 meg free in the address space, this is fragmentation. We can't allocate even the 1 megabyte 32-bit stack because there's no block big enough. So that's how we can verify that it's fragmentation, even though we should be able to allocate around 300 more threads, given this number right here. And if we go to something called the fragmentation view, we can actually see this very graphically. So this is the address space. Let me zoom all the way out. And you can see there's lots of little tiny slices of white. And if I zoom in now and I click, what this does is serves as a map. So here I'm clicking on this thread down here, and then following it right there, there's the reservation part, or the guard page. There's the reservation. Then there's a gap, and then here's another thread right here of another thread stack. So this is wasted space right here of 192K in between. And that's just a side effect of actually address space layout or load randomization, ASLR, which was introduced in Windows Vista, where the process will randomly try to randomize the allocations of thread stacks to prevent malware from being able to know reliably where things are. And unfortunately, it causes this fragmentation issue at the same time, which may or may not be fixed in vNext. I can't tell you if it is or not. Now, file mapping, as I talked about, file mapping is a way for a process to treat files as if they were in its address space. When you allocate private data and you touch that private data, well, it's sure going to be right there. You can touch it. When you want to access a file, normally you have to do file IOs to get it. Read file, write file, reading into chunks of your address space. So you read file, make a modification in your private memory that you read that into, and then write file it back. With memory map file, you can say, system, pretend that this part of my address space is that part of that file right there. And once you've created that mapping, now when you touch your address space, you're really accessing the file as if it was there magically in your address space. This is the way that executables are loaded into memory. They're mapped into the address space. And so when Notepad first started up, notepad.exe was mapped into the address space. And then the first thread was created with a start address that pointed into that code section, one of those code sections like we saw in VMmap's image. And the thread starts executing there. Boom, it hits that first instruction. That causes a page fault. The system goes, this is a memory mapped file. I need to go fetch that page of notepad.exe, pulls it into RAM, connects that RAM piece with the virtual memory of that notepad process, and now says, OK, continue. And then that thread starts executing those code bytes that are sitting there in that page of memory. Notepad didn't even know that it was doing that. It just happened magically underneath the hood. And that's also used for data files as well. You can see here a data file being mapped into a process address space. This is, in fact, how most data-intensive applications like SQL Server will work, is they will map the data into their address space, mess with it, and they know that when they're messing with it, that it will eventually get it way back to disk. And actually, there's APIs where you can say flush and force it back to disk that I'll talk about in part 2. And shared memory is also another way, by the way, to do mapping, where I can say, memory manager, I want to share some memory, allocate some shared memory. It allocates a chunk of shared memory in my address space. You saw some of those shared chunks in Notepad. And then what it can do that is name that shared memory. I can name it foo. And then another process can start up and say, memory manager, map foo into my address space. And then that part of the address space of the other process is mapped into this address space. And now, like I said, we can talk to each other through our own address spaces. There's many examples of memory map files in the system, and I mentioned some. Let's see, a process in Windows that makes heavy use of this is CSRSS, which maps a bunch of true type font files into its address space. And you can distinguish executable mapping from a data mapping in Process Explorer by adding this, wrong column, mapping type here. The mapping type will be either image or data. If it's image, it means it was loaded by the loader and it's mapped for code execution. If it's data, it's going to be accessed as a data file. And so if I select that, mapping type, and move this over, and then sort by data, you can see font files and true type font files, a bunch of those mapped into the address space. With Process Explorer, you can also get some view into address space usage for files like this by adding the base address right here, image base address. So this is the address at which the file is mapped into the address space. Same thing you see in VMmap over here. And with Process Monitor, if you're interested in watching files get mapped for executable access, or get mapped for, or data files from disk get mapped into an address space for data access, Process Monitor will show you those mappings. And the way that I'll fire Process Monitor up, and what I'm going to do is, in Notepad, I'm going to do a little experiment with Notepad where I will open the File Open dialog. And now I go back to Process Monitor, and let's set a filter for just Notepad. And I just want to see image loads. So let me deselect all this stuff and set a filter for just image loads. And there's all the DLLs that got loaded when I did that. And, well, actually, some of them got loaded and then unloaded. You can see because they're loaded multiple times. If we can look at the stack even. Why was that DLL loaded and unloaded so many times? Well, this looks like it was extracting icons from it to show us in that dialog, the file picker dialog, and it probably unloaded the DLL, saw that it needed to get another icon, saw that it was in this DLL, loaded the DLL again to pull an icon out of it. So that's a look at file loading, file mapping. One of the things that VMmap can do, and this is kind of cool, if you want to see the impact of a process, of an operation on a process on the system, you can use differencing mode. You can perform an operation, take a snapshot with VMmap, perform another operation, take another snapshot with VMmap, and then look at the difference between those two snapshots. That will show you the amount of different type of address space change. DLL is getting loaded, DLL is getting unloaded, memory getting allocated or freed in this differencing view. Let's go take a look at a differencing view. I've got that VMmap that had Notepad loaded into it, that one I just did the file open. Now, how big do you think that number is going to get to now when I did that file open? It's at 53 meg now. That's where we started. When I press F5, what do you think it'll be? Anyone want to guess? 100? Anybody higher than 100? 150. Got it, 150, 150, 175? All right, let's see what it is. Oh, close. 109. Now, what is that 109 made up of? Control D. Let me go to the top, select this, and here's our breakdown. So this also shows you, this right side is where it is now. This color in part is what it grew since the last snapshot. So it grew by over 50%, as you know. And most of that growth, again, was the DLLs, these image mappings. If I click on images, you can see there's a bunch of green. Those are all those DLLs we saw get loaded in Process Monitor. These are ones that are still loaded at the time I did that second snapshot. Now, the ones that are purple and that still show up here, that means that something changed. What changed? Well, a great example right here. An NTDLL, the only number that's not blank is private. And that means that actually, I think I did an F5 by accident. But that private means that it created a copy on write page of 4 kilobytes. It modified a page of memory, and then it became private out of it, the NTDLL image mapping. So that's the change there. Let's take a look at some of the other changes. Well, virtual memory, here's all the virtual ALECs that were made. Lots of small chunks, by the way, which isn't good, as you know, because it's going to lead to that unusable memory. In fact, we grew unusable memory by 4.6 megabytes in that process. I mean, not a big deal for Notepad, because Notepad isn't, going to probably worry about exhausting its address space. It's still got a long way to go to get to 4 gig or 2 gig on a 32-bit system, but still. And then heap. And you can see it created some new heaps in that process. Some new heaps were probably created by some of those DLLs. Some DLLs say, hey, I'm too good to use your heap. I want to use my heap. And so I'll allocate its own heap. And that's what we're seeing there, some private heaps for some DLLs. One of the other things you can do with VMmap is trace an execution of a process. What that does is gives you insight into the heap usage. You'll be able to look at the stacks. And you also get a timeline. Actually, you get a timeline even with VMmap not in tracing mode, which I'm in. I'm not in tracing mode right now. But if I press F5 and then I do something else like, ooh, let's see what happens if I close this dialog. What happens? How much gets freed up? I'd press F5. Not much. In fact, I'd basically, here, let me go to the timeline here. So I want to see a difference between this and this. I select those two. And how much did we shrink by? 1 meg when I close that dialog. So almost everything that that dialog brought in stayed in. So you might be thinking, well, that's a big waste, and why does Notepad get so big for this, and what's the, just a simple dialog box? Well, that dialog box is Explorer. I actually set Notepad as my shell because I can do everything in Notepad that I can do in Explorer because I've got Explorer right there. So when I log into the system, Notepad launches, and then I can go and launch processes from that dialog box. I can open files, and I'm good to go. And so it doesn't unload it, probably because it expects that I might open that dialog box again, and so it keeps those mappings current. But I can look at the same thing with tracing mode. Let's do that. So I'm going to start VMmap. Go to Launch and Trace New Process, and I'm selecting notepad.exe again. And then I'm going to go back to that second notepad, do a Control Open to do that, open that same dialog box. Come back to this VMmap, go to the timeline. Here's now what we can see. It's taking automatic snapshots. And let's see that if I click right here, now I'm just looking at that snapshot in time. And if I click on heap, here are all the heap allocations that happened that were active at that point in time. Here's a large heap. And if I click heap allocations, here are all the sub-allocations from that heap. Let's see what the biggest one looks like. Biggest one's about 132K. And if I double-click on that, I see the stack that allocated it. And we see that Notepad called show open save dialog, which then called internal dialog box, which called jump to initial location, browse objects, which blah, 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 safe MSQ, post NL. There, we finally get down to the allocation right there. So that's what you can see with VMmap's tracing functionality. So everything we've talked about up until now has been process committed memory. But process committed memory is related, has a relationship with the system commit, or the system commit limit, system commit charge. What is the system commit charge? Well, some types of virtual memory are counted towards something called the system commit limit. It's system committed virtual memory. That type of memory has to be backed by either RAM or the paging file. That means the system commit limit, the total amount of system committed memory you can allocate, by definition, can be at most the size of your RAM plus the size of your paging file or files. Sum those up. And that is the system commit limit. Now, what kind of memory gets charged against the system commit limit? What type of virtual memory? Private allocations and shared memory allocations. Anything that cannot be backed by a data file or an executable file on disk is charged against the system commit limit. Let me explain why. When Notepad's running and the system says, the system loads Notepad's DLLs into RAM, but then decides it wants to use that RAM for something else. What does it do with the copy of Notepad's file that's in RAM? It tosses it, right? It doesn't need to save it anywhere because it knows if it needs it again, where can it get it? Notepad's file on disk. So it just throws it away, says, yeah, if I need that again, I know where to go get it. But what if Notepad, if I opened a file and loaded it into Notepad, Notepad allocates virtual memory to load that file. It's going to actually show up as virtual Alex in VMmap to store the contents of that file. Now, if the contents of that virtual memory are in RAM, but then the system says, I want to take this RAM and use it for something else, what does it have to do with that? it has to save that someplace. Where can it save it? The paging file, because it needs to get it back. It can't toss it like it did with Notepad.exe, because if it did, you'd lose the file. So it pushes it out in the note paging file, and later can bring it back. So any memory that has that characteristic where if we wanted to get rid of it, we'd have to save it to the paging file, is system committed memory. So exes don't count for the most part, except for the copy on write parts, like that 4K page we saw in NTDLL that was modified. That modified page now, it counts against system commit. The system actually pre-charges the copy on write pages that, again, I'm going to talk more about copy on write in part 2. But just in case, if I said I want to allocate this amount of memory and I mark it copy on write, the system is going to say, just in case you modify that, I need to make sure that I've got enough system commit to handle that. So I'm going to charge that against the system commit limit. And if we run out, then I'm going to fail your allocation, because I can't promise you that I could save that data. This is, Windows has got a very conservative memory manager. And that's kind of the reason that it calls it commit, because it's making a commitment. I'm committing to you. Windows is not commitment averse. It says, yeah, I'll do it. Let's do it. I will make sure that this data can come back. You know what? Let's see what's going on with my TS login that I forgot about a long time ago. Because I'm going to show you. Yeah, timed out. I need to re-log in. Because what I'm going to show you is the effects of what happens when the commit limit is reached. And then we'll talk about changing the commit limit. While that's logging in again, here's a second page to this, which I tell it the machine that I want to connect to. And it's this website that actually the portal's been slow the last few weeks. I don't know what's going on. It's obviously not running on Windows Azure. While that's loading, why don't I show you some pictures? These are out of memories that happen out in the public. So this one happened, you can see at an airport. So lots of, probably when this happened, that display froze. So I'm guessing a lot of people missed their flights that day. This one, kind of interesting because that's that close up. This one happened at an internal Microsoft conference that happens at the Seattle Convention Center called Tech Ready. I gave this talk, and literally 10 minutes after the talk was done, a guy walking into the hotel next door that had been in the talk said, hey, take a look at what I found. And it's that right there in the hotel lobby. It's a Paris hotel and casino. Macy's. Let's see if this is ready for me. Yeah. What? Okay. Okay, and I think I've got one more. Yeah, this one. It's a billboard. Actually, Dave Solomon snapped this picture. He was driving down the road. He sees this. He pulls over to the side of the road, jumps out of the car, runs over, finds a ladder, and jumps up to see if he can find the switch to reboot the machine. We're back to step one. All right, so let's have fun with Windows. Would you rather do this on Windows 7 or Windows XP? Something new? All right, let's do that. We'll break something new. Doesn't make me feel good about breaking Windows 7, but we'll do it if you want to. Because Windows vNext is way better. It's unbreakable, Windows vNext. Does Windows vNext come with Notepad? Oh yeah, and it's an awesome Notepad. Yeah. I mean, you saw the improvements that went into Windows 7's Notepad. It's way faster than the old one. All right, what is going on here? Move that to the side. Finally. And I think I've got a VM here ready to go. Let's do view full screen. And let's run Process Explorer. Now, Process Explorer, I didn't really harden against out of memory, so this could be a little embarrassing. But one of the things that you can see with Process Explorer is the commit history right up here in this top chart. And so I'm going to run Testlimit, Testlimit-64, -M. And where is Testlimit? Oh, this is 32-bit, -M. And we've just leaked 2 gigabytes, and now you can see, boom, we just went from 482 megabytes of commit to 2.4 gigabytes. We went up by 2 gigabytes, as you'd expect, with that 2 gigabyte of private commit that just Testlimit just made. Let's do that again. Let's do that again. And again. And again. Oh. Let's see what else we can't do. Well, it's actually, the paging file can grow, maybe, in some cases. But at this point, the system starts to act a little interesting. And under XP, you never see that paging file is too small. You just see more random stuff. Let's see if I can run disk management. Specified procedure could not be found. So you start to see weird. Let's run Explorer. Oh, there's, yeah. OK, so that's an interesting error dialog box. And I don't know what that is probably might be saying. It could be saying press the button to wipe your machine or something. Let's run IE. How about getting started? Can we get started? Control panel. Oh, the control panel is there. I don't know what that button is. So you get the idea. Actually, Process Explorer is, I think, gone now at this point. In fact, everything is gone. So now, yeah, it's like a coloring book. And the cool thing is, though, let's see if we can close these things. If I can get a right context menu. Oh, all right, so never mind. So you get the idea. That's the way the system behaves when you run out. So let's talk about why you would want to change that commit limit. We saw a certain commit limit there. Size of the paging file plus size of the RAM. So there's a few ways, obviously, you can change the commit limit. One is add RAM. The other one's add sizing to the paging file or add paging files. So how do you do this? Let's go see where this magical setting is stored. It's in here, computer properties. All right, you really have to know what you're doing at this point. So this scares away the newbies, advanced system settings. And then you go to the advanced tab here. This is second warning, your second warning. Do not come here. And then you go to performance and you go to settings. And here, your third and final warning. And then you go to change. And it says, oh, yeah, I'm doing it for you anyway. So it automatically changes, sets the sizes. And I'll tell you what the sizes are in a second. If you want to override that, of course, you uncheck this and then set the sizes. So what are those sizes? Well, the default configuration for system managed, the minimum, you'd think, well, first of all, when you first get to this, you're like, system managed. I wish I knew what that algorithm was, because it's probably really tricky, intricate, based on a lot of heuristics. System's watching the way the system's behaving and tuning things. What is it? 1.5x RAM if RAM is less than 1 gig, otherwise it's RAM, is the min. And the max is 3x RAM or 4 gig, whichever is larger. So you can tell a lot of time and energy went into the tuning that. Performance team was busy for a long time, and they actually got that right several releases of Windows ago. They haven't had to change it since. It's just such a solid algorithm to size the paging file. Well, but what really is that doing? Where's that? What do those numbers mean, 1.5x? First of all, how do you measure the system commit limit, system commit usage of your system, to know if you're anywhere near the system commit limit? There's a few performance counters, committed bytes and commit limit, and you can see that task managers called these things various names in the past, unfortunately. In XP, the commit charge was labeled PF usage. In Vista, they expanded the PF to page file usage. In Win 7, they changed it to commit. And in Vista, in Win 7, they show the commit limit after the slash. They don't even label it, just assume that you know what that is. Well, then there's commit is getting better, but it's still a pretty sucky name for it. It's really system commit, not commit, and it really should have the limit there called out explicitly. And by the way, if you know the guy that wrote Task Manager or owns it, please let me know, because I haven't been able to find him. And that's one of the things about working at a place like Microsoft is that sometimes you can't find these people. And the Task Manager guy, he's made quite a few interesting decisions that I'd like to talk to him about. Well, really one of the ways that Process Explorer will show you, as you saw, is if you go to the System Information Dialog, it will show you the system commit, limit, and usage in a few different ways. The chart at the top is the system commit usage currently, and here you can see the current system commit charge, the limit, and you see this other number called the peak, which I'll talk about in a second. The current is about 60% of the peak. The peak was over the limit is actually 118%. Why could the peak be bigger than the limit? Anybody know? Why would the peak be bigger than the limit? Somebody said something over here. The page file grew, and then what? And then shrunk, right. Page file grew at some point, and then it shrunk again, and now so the peak went above what the current limit is. Because the limit changes according to how big the paging file grows. I showed you this. Now, to size the paging file, what really matters? It doesn't matter how much is in use right now. It doesn't matter really how much RAM you have. Unfortunately, that automatic sizing algorithm is the worst kind of algorithm there is for sizing the paging file. And unfortunately, that's almost all the advice that you see out on the web is how big should the paging file be? Well, tip, set your correct paging file. How big should it be? It should be, multiply by 1.5, I think it says here. 1.5 or 3x, whichever one you have initial, 1.5x. And then here's another one. Actually, that one says it correctly. There's another. You can find this all over the web. This is on, unfortunately, Microsoft TechNet place, where this guy probably is from Microsoft. Oh, yeah, here we go. Thanks, David. So so everybody email him right now. The amount that you should change it to is really based on how much your system needs. We saw that if I run Testlimit-M 1024-C1, it just needed 1 gigabyte of system commit. If I ran Testlimit with 30 whatever, it would need 3 gigabytes. So how big should the paging file be? Well, right. How much do in the course of me running Windows, what's the max that I want to put on that Testlimit command line? If I was interested in sizing it so that I could do those kinds of experiments, I would set it so that I could accommodate that system commit. In other words, I would say, is the sum of RAM plus the size of the paging file greater than that number plus some for the system to use? If the answer is yes, then I don't need to grow the paging file really. I might want to just to give myself some buffer, but if it was less, if I knew it was less than what I wanted to allocate, then I knew for sure that I'd have to create a bigger paging file. How big can I see what, since we're not normally tuning our apps by saying exactly how much memory they should allocate, how much memory can I commit, can I determine that the system is needed since I booted? If you run under a standard type of workload, this is the peak number that I've been talking about. This is the most that I've used so far since I last booted the system in terms of system commit. And you know when that happened when very start when I ran that Testlimit and that -m, and we saw it grow the paging file and the system running out of virtual memory. Those out of virtual memories were temporary because the paging file had filled up, and then it was starting to grow because I've got it on the adjust mode. So it starts at a minimum of 1.5, and then it goes up to, in this case, at 4 gigabytes of paging file size. I didn't reach the max commit limit, which on this system would be 8 gigabytes. 4 gigabytes of RAM plus the 4 gigabytes of paging file. So if I wanted to size my paging files, I would size it to accommodate that. Which I've got 4 gigabytes of RAM, I would need to have a paging file size a little over 2 gigabytes to accommodate that. It turns out the more RAM you have, the smaller the paging file size you'll need. So these formulas that say take your RAM and multiply it, that's really totally broken, utterly going the wrong direction. And obviously based off nothing, factual. But if you want to multiply, do that exercise. If you really want to tune your size of your paging file, make sure you got it right, then multiply that by 1.5 or 2 to give yourself some buffer. The other thing you got to worry about is that it's big enough to hold a kernel crash dump. If you're interested in capturing a dump of the system when it crashes, by default now, since Vista, all systems are configured to do kernel dumps by default, how big does a kernel dump have to get? How big is it going to be on your system? That's something else that you need to do through experimentation. So one way to do it is take your system under load, run a tool like Not My Fault, which crashes your machine on purpose, which I'll show you tomorrow afternoon if you come to the case and then explain, and then see if that fits in the paging file. Oh, and one more thing before we wrap up and take a break before part 2. Can Windows run without a paging file? Sure. I can set a paging file size of 0, and Windows will run just fine without a paging file. Will Windows run faster if I have a huge paging file or no paging file? Does anybody know? Because there's lots of misinformation out there, too, like don't make your paging file too big. It'll slow down Windows. That's true. That's right. How big your paging file doesn't matter. It's how often it's used. I can make a Jagundis paging file. If I'm never paging, I'm not impacting my performance of my system in any meaningful way. Actually, the opposite happens. If I set a paging file size of 0, I'm probably hurting performance. Because I got to go to disk every time if I have no paging file? No. I still have a system commit limit that I can't run more. But if my load fits within RAM, my system commit limit fits within RAM, then I'm fine. The problem is that the least frequently used stuff has no place to go. One of the things that you would like to use RAM for is for the most useful things that your workload needs. And that might be the private data it allocates that's backed by system commit, in which case setting your paging file size to 0 probably doesn't buy you that much if it's all of that system commit's active. But in most cases, large parts of it are going to go cold for long periods of time. And that cold part, you'd like to say, I don't want to store that in RAM. It's just taking up space that I could be using to cache file data, because my app probably is accessing files, and I'd rather have those cached in memory than this cold private bytes. So if I create a paging file, Windows can send that stuff out to the paging file, making space in RAM for cached files. So actually, you will hurt performance by having a smaller paging file or no paging file rather than going the other way. And so that's the lesson of paging file sizing. That brings us to the end of part 1. So let's take I think it's a half-an-hour break. And then we'll come back and pick up on physical memory management. And if you're not here, I will know that you're not here.